Hello and welcome everybody to the Israel Geological Society annual meeting 2016 in Eilat. I'm very honored and pleased that we have with us a very distinguished speaker for the opening lecture of this meeting. And I would like to ask Moti Stein to come here and introduce our speaker, Bill Griffin. Thank you, Moti.
Hi, good morning. It's really a big honor, and I was excited when Yaron told me that actually both of you come here and give talks in this meeting. And so I welcome his big assignment, Professor Bill Griffin from Macquarie University in Australia. But actually, Bill started his career in Norway. And I think that between 1980, if I remember well, to 1988, he was a professor in the University of Oslo. But then somehow he diverted to the industry and was also a chief scientist in, I always forget the name of this company, but it doesn't matter. But then he was involved in many fields which are related to EBSD petrology, development of mantle dynamics, and lower continental crust. And I want to say something personal here, because when I started together with Professor Tzvi Garfinkel my studies on the xenoliths and the lithosphere beneath Israel and this area of the Nubian Shield, then the great name in the literatures at that time were Ken Ringwood and David Green. But then we came across, and the papers were always Griffin, right? And O'Reilly and Griffin, and these were the basic papers that we actually read at that time when we tried to study about works that were done in the world about mantle xenoliths, the lithosphere, and the lower continental crust. So I think that if I go over the field of research of Bill Griffin, they include petrology and geochemistry, the deep crust, the lithospheric mantle, magma generation, and metasomatism. I think that Bill was involved deeply in the development of the field of mantle metasomatism, development of techniques for in situ measurements of trace elements, isotope composition, and applications for mineral perspectives in the industry and so forth. He got a lot of awards, and I think that he has something like 400 papers and thousands of citations, so that's something really amazing. And he is a fellow of the Norwegian Academy of Science and also a fellow of the Royal Norwegian Society of Science and Letters. You have to explain to me later what is his letters, right? Probably literature or something like this. Right? So, and then he was also the chief editor of Lithos from 1973 to 1986. And then he actually moved also to activities in China. He was one of the people that actually initiated the new geological survey of China and other activities. So I just want, I looked at the papers and I told myself, let's just bring one of them. And this is my personal choice. Okay, so remember, this is only my personal choice. And this is going far away. And my personal choice is Griffin and O'Reilly. Both of them are here now. 1987. Is the crust mantle boundary, geology 15-2441, 244. I recommend to all of you to go back to this paper and read it. Thank you very much for coming here.
I think I turned it on. Yes, okay, good. Okay, Shalom. And thank you very much for inviting us, and thank you, Moti, for that very embarrassing introduction. Okay, this rather strange title actually reflects a kind of a geological journey that we've been on for about 5 or 6 years, and it's started off in Tibet, and we wound up in Israel, and now it's looking like we're going to have to go a lot of other places as well. But in any case, this is we started off in Tibet because we were interested in the question of, if I can make this work, there we go, in the question of continental collisions and what happens to the mantle in continental collisions. And we thought that, well, you may as well go and look at the place where you have one of the world's biggest continental collisions, and that, of course, involves this, if I can again make this work. No, it's not. I'm sorry, I'm having a lot of trouble with this thing. I'll have to just start over. Okay, here we go. And the laser pointer is somewhere here. I got it. No, I don't. Okay, I'll have to use this. If you're going to watch this little program here, notice way down at the bottom, India and so forth are just detaching from Gondwana. And watch it, as you know, it goes very, very rapidly north, and it whacks into Asia, and it's still doing it. And so this is an ongoing continental collision, and you can study this in many ways. This, of course, produced the Himalaya, which is down here, but the whole process was sequential, and there's a whole series of terrains that build up Tibet, and each of them has a suture separating it from the next terrain, and each of these sutures carries large amounts of ophiolites. And these so-called ophiolites, I'm going to use that in parentheses, and you'll see why. Because, but the interesting ones, the ones we'll really look at today, are these yellow ones down here at the bottom. They are in place quite late. They're very interesting, but the most interesting one are the ones to the far right here, because they've been the most studied. And that's the famous Luobusa peridiotites. Now, when you start looking at the peridiotites, you have to go up very high. This is 5,000 meters, and they're beautiful things because they have, I'm going to try this again. It's going to, nope, sorry. Okay. It's going to, what you're seeing here, the sunlight is nicely outlining, let's say, can you tell me what to do with that? The sunlight stripe there is nicely outlining contact between one of the peridiotites and the Triassic schists that are to the right. And this is a thrust contact. It is going to work, is it? This one? Yay, we have it. Okay. And the reason all these roads are here at this altitude is because in some parts of the peridotite, like down here, you see a lot of cuts and tunnels and so forth. This is the Chinese method of mining chromite. It's extremely dangerous and not to be recommended for the faint-hearted. The point about that is that this is a place you can go and you can study chromatite deposits and so forth. And these are typical of ophiolites. You find them in ophiolites all over the world. And the usual explanation for them is they form just below the oceanic crust, 5 to 10 kilometers deep perhaps, and they are a shallow phenomenon, and thought to be formed by ophiolites being abducted up onto the crust and so forth. And they're usually, the chromatites and things are right here, at the upper mantle, lower crustal boundary. Now, the problem with that is that when you look at the so-called ophiolites in Tibet, they actually, all along the Arlington suture, contain diamonds. Okay? This is a problem because these are supposed to be shallow rocks. But these are very strange diamonds. And these diamonds have been rejected by an awful lot of the scientific community, including originally me, as being synthetic contamination, anthropogenic. I even wrote a paper where I said this. But it's not true. We've had very close looks at these diamonds, and there's an article in EPSL late last year by Dan Howell, which will give you all the details. But basically, although they look synthetic, they are not. They are natural diamonds, and they are being extracted from these peridiotites. These were all extracted by our Chinese colleagues, and that's perhaps one reason there's been a lot of skepticism. But this one we extracted ourselves from a hen specimen that I personally collected and has never seen a saw or a drill bit or anything like that. So, and we have about half a dozen more of them after that. But that one was very exciting. So they are real, they are natural, and so forth. And that immediately gives us a problem because these are all spinel peridiotites. And as you know, the diamond stability field is down here. And if you look at where the spinel garnet stability line goes, it's up here. So if we have diamonds, we should have garnet peridiotites. But so there's a real disconnect here. We have shallow chromatites, and you take them apart and you find diamonds in them. but there are no garnets in the peridotite. And this is one reason we started getting really interested in these particular peridotite. Now, however, there is a lot of other evidence besides the diamonds that these things have been very deep. Larissa Dobryshnetskaya has produced a lot of papers about this one particular sample, which has things like coesite, and which apparently is after stishovite, sitting in a reaction zone and so forth. It's a very strange little sample, but it still has to be fitted into the story. There's other evidence, and that is one of the most interesting ones is in this stuff here, because I'll flick that up here. The chromatites in these things contain a lot of exolved needles of coesite, enstatite, and especially diopside. The problem is that you can't put calcium and silicon into chromite. So it was proposed quite a few years ago that, in fact, by Yamamoto, that this represented exsolution from an inverted calcium ferrite structured spinel. Okay? And to do that, you have to get down into the transition zone. This has recently been confirmed by a very nice study that's been going on at the University of China, the China University of Geosciences in Wuhan, which I hope will be sent to a journal next week, where they've confirmed experimentally that you really do have to get this high pressure polymorph in order to have calcium and silicon in there, and then you can exsolve it very easily when you bring this up and it inverts. So this means we have more evidence that these things have in fact been, oops, sorry, wrong way, at depth. And so this is the idea is you have calcium ferrite structured thing, inverts the spinel, and all the stuff comes out. Now, but recently one of our Chinese PhD students has discovered some more evidence. It turns out that within some of these peridotites, which fortunately are very fresh, unlike most ophiolites, by the way, you find these, occasionally find these remarkable symplectites of spinel sitting inside single crystals or double crystals of orthopyroxene with a little bit of clinopyroxene sometimes. And if you do EBSD on these things, you find out that in fact all of the orthopyroxene and all of the spinel and all of the clinopyroxene each represent a single crystal. Okay? So they look like a breakdown product. If you reconstruct them, which you can do in various ways, but if you do, what you find is that they are in fact appear to be the breakdown of garnet. And that garnet, when reconstructed, is very majoretic. And it would represent pressures well down into the transition zone. So this, I think, is the missing link, that we did have garnet peridotites, but they have come up rather rapidly, and in some cases have preserved evidence that they were down there. Now, so we have evidence then for a shallow origin. We have evidence that they've been somewhere down very deep, probably in the transition zone, and we then have them coming back to the surface. So we can then start setting up a petrogenetic grid and see what we think has happened. And we think that basically these things started off up at very shallow depths where we have serpentines. They would have, going down, these serpentines would have been converting to things like phase A and phase D and so forth, the dense magnesium silicates with water. And ultimately we get down past the forsterite, Waldsleyite transition, and then we'll get down to ringwoodite and so forth, somewhere in the transition zone. Now, that, if I just blank out those lines, there's a few other things we can use. We know we have to be deeper than the diamond graphite stability curve, and we also have coesite stishovite line there. We have the coesite stishovite line there, and we have a few other lines that we can put on here. For example, this is the kyanite going to corundum plus stishovite. We're not sure this happens but it may have. I'll show you why. And I don't think we go deeper than that, because the chromatites contain a lot of beautiful crystals of diopside scattered through them with beautiful shapes constrained by the enclosing mineral. So it looks like we had plenty of diopside still there. So that means that we're now able to reconstruct the PT path, and it looks sort of like this. First we take it down into the transition zone, and we have things that look like phase D as inclusions in the chromatites, but frankly I wouldn't believe that unless I told you. But they might be, but we haven't confirmed that yet. The problem is once they get into the transition zone, they're coming in at this kind of temperature. And then if they're sitting in the transition zone, then of course they have to warm up, depending on how long they spend down there, because it's about 1,500 degrees down there. And so we think that they're going to heat up along a path something like this, and maybe go through a field that looks something like that. And the question is, how far do they really go? And that's a bit difficult to say, but we do have, I'll come back to this in a moment, within the chromatites you do have little balls of native iron and all sorts of things. And so we think that we have been looking at the melting of iron, which would take you up to this kind of temperatures. Now, fortunately, that's also what the mantle adiabat would say you should be reaching within the transition zone. So then we have to bring it up again, and we'll bring it up, we'll try to avoid melting it, take it under the solidus, under the Harzbergite solidus here, because we don't see any real sign of much melting in these things, and then take it on back down to some low temperature and so forth. So effectively what we're doing is excavating these things up out of the slab graveyard, the transition zone. I thought this was a very difficult problem, but I went to our geophysical modeling people and they said, we solved that years ago. And in fact, Louis Moraci published a very nice picture, a couple of movies, which I'll try to play, in Nature 2014, where what he's looking at is the, before this starts moving, is the subduction of a slab. Here comes the Tethyan slab, here comes the ocean, but he's putting a little bit of ribbon continent into this, because what they're studying is what happens when you have little pieces of continent colliding into the zone and the rest of it is still trying to subduct. And we think that would be very relevant to the Tethyan Tibetan part of the subduction story, because there's lots of little fragments coming together. So if we can play that one, let us pray, we'll see. What happens now is that, you see, once the little slab, once the ribbon continent hits, the rest of the slab rolls back. And the rollback is really quite spectacular. You're seeing this in 3 dimensions here. And this takes the slab right on down into the transition zone, but it also creates a big hole here. So something has to give. And you see this best, I think, in this one, which is looking at it from underneath. Let's see. There we go. Let's try again. Okay, try again. Where's the little button here? No. It's not going to let me do this, is it? Unless I'm very lucky. There we go. Okay. Now, we're looking at from underneath. There the slab hits, or the continent hits, and you see how everything's pulling back. And you see all the little pieces flying through into here? Everything's coming roaring up out of the depths and whipping out into the hole, which is being created. Okay, if you look at that in a slightly more, shall we say, a calmer two-dimensional view, then the process would look like this. And you can see the little arrows here. In detail, what happens is that you very rapidly develop a kind of channelized, as the slab hits the transition zone, you develop a channelized flow zone here, which is moving very, very, very rapidly. And that is, if you combine that with the natural buoyancy of an old piece of mantle that has been subducted into the transition zone, then you have a recipe for rapid transit. And the estimates range from about 6 million years to 10 million years to take something out of the transition zone and up to the surface. And that's very handy if you're trying to do what we're doing. So here's a slightly more, a slightly more graphic view. I did this first. If we put a body down, a buoyant Harzbergite down here, and then watch it how it behaves during that development, it'll be moving up that channelized zone here, and it will finally reach the surface there. And so we think that that's what happened to Luobusa and probably to all of the other periddotites along this zone. And it turns out that this is also probably the history, by the way, of the so-called ophiolites that are in the northern end of the polar Urals, which look very similar in every way. And they also have diamonds, and they have all the other minerals that we're looking at. So it's a process that is not unique to the Tibetan situation. So in Tibet, we happen to know a bit about how this all developed because we think we have both zircon data and rhenium osmium data to suggest that the chromatites actually formed around 375 million years ago in a super subduction zone type of environment. We think that they were probably down here for something on the order of 230 million years. And we have also, there's beautiful big osmiridium nuggets in these things, and when you do the osmium isotopes of those, they tell you that they're very old, but they have probably re-equilibrated down here and at about 200 million years. And then we have to bring them up rather rapidly. We think they were in place probably around 130 million years ago, and they're then cooled off very rapidly, and their thrusts, they start getting thrust up onto the continent about that time with the main collision. So our 350 million year history, we start off somewhere in the northern hemisphere. We have some 200 million years sitting down there, and then we bring them back up from the arc. This is way down at the bottom here, isn't it? Up into a back arc basin. And we think a lot of these things probably formed the seafloor in those basins. One of them apparently formed a seamount whose elevation is above the trench, or the basin bottom is estimated at something like 2 kilometers. So this is stratigraphic things, which I don't know very much about. Okay, so we thought, good, now we've solved the problem of the low pressure origin, the high pressure minerals and so forth. But there's another issue with these periddotites, and that is that the Chinese for years have been working on Luobusa, taking tons of material, crushing it up, and picking very laboriously through this. It's very great. In China, you have lots and lots of student power, you know. You can just sit and do this. And what they have discovered over the years is this amazing mineral assemblage. I mean, hundreds of things that have never been seen anywhere else previously. And they are, the thing they have in common is they're super reduced. You have things like native silicon, native iron. This is silicon carbide. And these things are all telling you that you have very low oxygen fugacity. And a lot of people will argue that you can't do this because the mantle doesn't have oxygen fugacity that low. Right? The general wisdom, here's a field showing all of the estimates we have for mantle rocks, and they sort of bottom out at the iron leucite buffer here in terms of oxygen isotopes. of FO2. And so, you know, what do you do with something that requires conditions that are way down here somewhere? And there have been a number of rather strange arguments involving, you know, low temperature origin for these things or whatever, and none of which seem to hold much water. And it's obvious that this can't be the condition of the entire mantle, but it has to be some kind of localized environment. But what? We were working on this, trying to figure this out, because we have the silicon carbide, there's native chromium and Luobusa and so forth. And so we knew we were down here somewhere, and we didn't know where to go from there. So we started studying the silicon carbide to see if we could find anything out about that. And while we were doing this, a Russian friend said that you really should contact this mob in Israel who are getting very big silicon carbides, because if you ever look at silicon carbide from mantle rocks, including the Tibetan ones, 100 microns is a big one, yes? And so we said, okay, you know, so we wrote to Shefa Yamim and saying, you know, we perhaps, you know, get a bit of this stuff to look at. And so we met with a wildly enthusiastic response, overwhelmingly enthusiastic, I might say, and this is still going on. And Shefa Yamim, as you probably all know, have been doing exploration in this general region here and looking for sapphire, ruby. They're finding all sorts of things. I'll come back to this one later. And the silicon carbide. So this was kind of an interesting opportunity, but it really shows, as I say here, the serendipitous nature of science. You start off to do one thing and wait till you see what you wind up next. It's really amazing. Anyway, so there's the placer output from Shefa Yamim, all sorts of things, including these gigantic moissanite crystals, sapphire, rubies, diamonds, you know, you name it. Okay. Now, we started studying the silicon carbide, but then we got questions. Vera Toledo sent us thinking, couldn't you tell us something about the corundum as well? Oh, yeah, we do it with your corundum. Okay, fine, that's good. And that turned out to be, that has turned out to be a real gold mine of scientific interest. And it's helped us to understand what might be going on in Tibet, strangely enough. So this is what we originally were, as a shorthand, we call it non-gem corundum. I think a nicer name is caramel sapphire, okay? Each fragment, and these come up to about 2.5 centimeters across so far. You haven't looked in the real size fraction yet, okay? And so it turns out that each of these is actually an aggregate of many smaller grains. And what you're seeing here is these dark things are actually little pockets of melt trapped within and between the grains. And they outline the crystals that are this sort of size. And when you start looking at that in detail, you get some spectacular information. This is CL imaging, and it's showing the zoning of one piece here. And this is, yes, this is 500 microns down here, so this is a pretty good sized piece. But you see there's zoning in here, which is clearly outlining some sort of growth pattern. And the differences in the CL brightness are caused by titanium substitution. And we're talking substitution up to very high levels. And I'll talk about this in another venue later this afternoon. I'll go into a little more detail. But I wish I had a color picture because the luminescence is actually brilliant pink grading into red. So they're very nice to look at. But when you look at it in detail, you start seeing that these crystals actually are growing as hopper crystals. You see, they have cavities on the faces, they have holes in the middle, and these dark holes are where you actually have some melt, and the titanium enrichment in the corundum is very high. And if you then look at some of these larger pieces in an EBSD image, which is sitting over here, each of these domains here consists of lots of small crystals, but the similar color shows that all those crystals have the same orientation. In this case, it means their C-axes are parallel. And if it's a little bit different color, it means the C-axis is a little bit different in orientation, and some of them are much different. So this is pretty characteristic of hopper growth. And hopper growth is something you can do in your kitchen if you want to do it with salt or with bismuth, for example. And hopper growth simply means that the edges of the crystals are growing much faster than the centers of the faces. And this is usually an indication that they're growing under supersaturated conditions. They're growing so rapidly that they can't keep themselves filled in. And this, of course, gives us an ideal way to trap melts. And the melts turn out to be quite amazing because they are full of an unusually super reduced mineral assemblage, which I'm going to show you. This is effectively, we now know that it's not unique on Earth, but this is certainly the first place where anybody's been able to see it and identify it and study it in any detail. This would be what we call a typical type S assemblage. You have a calcium aluminum silicate glass sitting in corundum. This mineral here, the orange thing, is something called Tistarite, which I'll come back to later. This is Ti2O3. This is much more reduced than you will see in anything else on Earth in general. This, in fact, was not known on Earth previously. Some of this writing here, by the way, is for people who are not geoscientists, so please ignore it. Anyway, this turns out to be a key mineral, as I'll show you. But you have other things. You have pockets of what we call an A-type melt, alloys. In this case, it's titanium carbide crystallizing from an iron silicide melt. And you have other amazing things. This is the titanium nitride sitting inside of skeletal cavities in the corundum. There's titanium diboride, which has never been seen as a natural phase before, and so forth. Now, I said that Tistarite was a key mineral. And the reason for that is that it exists previously. Well, this is the type of material, and in fact, the only material. That's the type of material of Tistarite. That's a 25 by 10 micron grain, and it's in a chondrule from a yende, which is, of course, one of the most primitive objects we know of from the solar system. And it's inside some of these calcium aluminium things. Yeah. Anyway, the nice thing about this is that you notice the mineral assemblage. This is the Tistarite. This is titanium carbide, which I just showed you crystallizing inside these melt pockets. And of course, what's surrounding it is corundum. So this is as we said, this is heaven on earth, because this is a really remarkable mineral assemblage that only occurs otherwise in meteorites, and very primitive meteorites. And we know how to make Tistarite. That's why this is so important. You make Tistarite in the early stages of condensation of the solar nebula, and you make it in rather close to the sun at very high temperature. It's one of the first 2 or 3 minerals that might condense out of the nebula. Those things later get blown out here up to about 1 astronomical unit, where they can get involved with other stuff and get made into chondrites and so on. But they're in an environment of the solar wind, which is just hydrogen, and that's really neat, because if you want to reduce things really, really down far, you have to go to hydrogen. You don't have much of an option. And you can produce shock waves within the solar nebula will produce temperatures, it's hiding here, up above 1400 degrees. And that's the kind of temperatures we think we're dealing with. So we have these nebular conditions down there somewhere. If you come to the talk this afternoon, I'll tell you why we think they're forming in this depth range. And the problem then is, where do you get the hydrogen? I mean, it's not that easy, is it? We want to have hydrogen introduced into our mantle somewhere down deeper than 30 kilometers. This is the upper mantle. Now, one possibility is to do that is with a subduction system, because the subduction system works very well in terms of generating methane, hydrogen, and so forth, because you've got sediments which are being subducted, they're being degassed, and you can actually generate a lot of methane. And the evidence is actually there in fluid inclusions in mantle wedge periddotites. They're liquid methane, hydrogen, nitrogen, argon, etc. But all of those interesting things are isotopically, crustally derived. So you can say, okay, these are coming out of the sediments. Now, the problem that we have is that it's all well and good to say that we have subduction in Tibet, and we certainly did have subduction, so that's a possibility. But can anybody tell me they really believe that there was subduction under Cretaceous Israel? I haven't been able to find any literature to this effect. But so if you do know about this, please tell me. Okay. There's another linked possibility, which is that we're actually dealing with, if we go back to the Tibetan situation, that we're dealing with something like this, where we have our rapid upwelling channels pulling up deep earth fluids, deep mantle fluids. And in the deep mantle, a lot of people would argue that the mantle is metal saturated. And that, if it is metal saturated, then any place at a reasonably high temperature, any carbon, oxygen, hydrogen fluid is dominated by methane, and the second most abundant gas, if you like, is hydrogen. So if we can bring that stuff up and keep it isolated from the surrounding more oxidized mantle, then we have perhaps a way of generating this. And there's recently, very recently, come up some rather startling evidence that this might actually be much more common than what anybody would have guessed. The Tolbachik volcano on Kamchatka erupted for a couple of years starting from 2012. And when it finally calmed down enough, then our Russian friends went in and sampled it the eruptions. Now this was violent pyroclastic explosives to start with, producing a pumice, which is a basaltic trachyandesite, looks like that. This is real serious pumice. It's very, very gassy. These eruptions continued for at least 2 years. They're still going on a little bit, but they're giving out lavas now. They blew their top, and now they're a lot quieter. But when they went to sample these things, they found out that when they pick up the piece of pumice, it glitters at them. And the reason it glitters at them is because they're full of diamonds. And these diamonds are, as you can see, about, there's 50 microns, so these are about 250 microns across. Very similar to the ones in Tibet in every way. They have the same kind of weird morphology. They have the same color, greenish to yellowish. They have the same carbon isotopes. Like the ones in Tibet, they have very low degrees of nitrogen aggregation. Again, they look very much like synthetic diamonds, but the Russians have shown pictures of them in C2 and so forth and so on. Now that's really exciting, and it turns out that if you go back in the literature, the Russians have been describing diamonds like this from the Kamchatka volcanoes for several years, quite a few years in fact. And of course the Western diamond mafia sort of brushes it aside because it doesn't fit with the conventional model for making diamonds, same as they did with the stuff from Tibet. But here's the kicker. It turns out that also reported within the pores of these pumices are silicon carbide, no details given, and metals, native iron, native nickel, all sorts of highly reduced phases, and high titanium corundum, as I live and breathe, is the same assemblage. And so we tend to think that we now have a link between Tibet, Israel, and this sort of Kamchatka thing, where these extremely reduced phases, it's also concentrated in titanium corundum, are coming up all over the place. And so we may have then effectively two different ways of doing this, and I'm not going to argue for one or the other until you can tell me more about the Cretaceous situation in Israel. But we might have situations where we're pulling methane and so forth off of slabs, but we might also be in a situation where that kind of slab subduction is driving this sort of upwelling. Now, some people named Stein and Hoffman said that this Israeli, that the magmatism in northern Israel was driven by hotspots and have an ocean island basalt signature, which of course a lot of us relate to plumes. So I'm happy to think of maybe plumes coming up and bringing also with them a freight of highly reduced gases and so on. So in summary, I'd just like to say that we started out trying to understand continental collision, and then we went to trying to understand some weird microdiamonds, and I think we've wound up identifying a major new geodynamic mechanism, namely how to get these things up out of the transition zone. And the farther we look abroad, the farther it seems that this is a common feature of hard collisions. Not soft ones, but where you get really hard collisions. It means there's an awful lot of big pieces of transition zone material sitting around waiting for people to study them, which is nice. We didn't have that before. And we think we've identified a new mantle environment involving very large scale fluxes of methane, hydrogen, and so forth. As I say, truly heaven on earth. Okay? I'd just like to close by, I get to stand up here and talk, but it's the other people who do all the work. And these are people involved in the Tibetan project, and now some of them, like Jin Qiang Wang, are engaged in the Israeli project as well. And we have a few other people here, quite a rogues gallery. I'd just like to mention Sarah Gain, who's done an amazing job of all this, of taking care of our separations and so forth. And of course, we've had a lot of local help. So thank you very much.
Thank you very much to Bill Griffin for this exciting talk. I forgot to mention at the beginning of Bill's talk that his arrival here, as well as the arrival of Sue O'Reilly, is actually thanks to the generous contribution of Shefa Yamim, and I wish to thank the company for bringing these two great geologists here. Thank you. Actually, this issue of diamond exploration and gem exploration in northern Israel will be continued in the next lecture session in the Batsheva Hall. So if you wish to keep on hearing about this, it's a good opportunity. Does anyone have questions to Bill? Well, I have one actually. I know that you haven't been to the field just yesterday actually. I wonder how can you be sure that these are all actually products of the Cretaceous magnetism? You mentioned that these minerals are coming from placers, so they might have come as well from other volcanic exposures in northern Israel, not necessarily from the Cretaceous volcanoes of the Carmel.
The answer to that is simply that Shefa Yamim have done all of the requisite bulk sampling of the primary vent deposits that were originally identified by SAS, and these things are not placer. You're not looking at placers. They sampled the tuffs, the vent pyroclastics, and so forth, and find all of these things in them. In fact, the biggest ones are in there. Yes, so I think that's the best answer. Yeah.
Okay, thank you very much.